graphing exponential functions, and a graphing calculator could be very helpful to you. As you see here, well, as you look down the paper, you see that there's grids on here that we're going to have to graph with. But in algebra 1, one of the functions you explored was the exponential function. And by definition, the exponential function can be written as y equals b to the x. So I have a couple of typos here that I have to fix. But instead of a here, let's put b in there, just to be consistent. B represents the base. And it has to be greater than 0. If you think about what we did in our notes yesterday, the very last things that we said is that for it to be an exponential growth equation, b had to be greater than 1. And for it to be exponential decay, b was between 0 and 1. The input of our function is the exponent, which is x. And once we pick a value for x, it will determine our output, which is going to be the 1. So as we go over here to our grids here, especially make sure to ask questions if you have the Inspire and you're not familiar with how to use this. But what we're going to do is we're going to graph these 3 functions, and then we're going to look at some characteristics of the graph. So first of all, when we pull up our calculator, we have this screen for many of you, and I can show you how to use the Inspire, if that's what you have. The Inspire has the mouse on it. But we're going to go to y equals. On the Inspire, you're going to go to the graph function. So when you're in your home screen, you go to number 2, graphing. And then what we're going to type in is we're going to type in 2 and caret and then x. And x is the underneath the window. It goes window, mode, and then it says x comma t comma theta comma n. That will get your variable x in there. And then what we really want to know is what goes in this table. So we're going to go to second, and then we're going to go over here to the graph, and that gets us up here to table. So depends on your screen here, and we may need to pause the video and check screens. But oftentimes what happens is that the screen looks like this. But let me pause the video and I will check screens if you need help. So now that we've checked our tables, we can take these values here and we can fill them in. And what we see is that -2 is 0.25. And that -1 is 0.5. And 0 is 1. I'm reading straight off the table. I know I'm not looking at it, but 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And 2 to the fourth is 16. And hopefully you're reading straight off of the table. So we come over here to our graph now, and we get -2, 0.25. And we get -1, 0.5. And we have 0, 1, and 1, 2, 2, 4, 3, 8, and 4, 16. So it's going to go a little bit off the graph here. And when we draw our picture here, it roughly looks like this. But there's something else that we need to be a little bit sure of on here. And that is, even though my picture doesn't illustrate it as well as I would like, is we never touch the x-axis on this graph. And what I just drew in was a dotted line there, and it actually is representing the line y equals 0. And what that dotted line is an asymptote. And the spelling is A-S-Y-M-P-T-O-T-E. It is a line that the graph approaches, but never quite touches. It never quite reaches it. So we get closer and closer and closer to it, but we never quite touch it. So we have an asymptote on this graph at y equals 0. But I'm going to pause the video again. What I'd like you to do is fill in B and C on here, and then we'll come back together. We'll check our work and fill in the common characteristics. So let's check our answers. Here is the picture of y equals 3 to the x. Once again, I would like to point out that we, even though I can't draw it in very well, have an asymptote at y equals 0. Our graph gets very close to the x-axis, but it never quite touches. And when we look at graph C, the same thing happens again. We have an asymptote at y equals 0. So there are our pictures, and I think that you could agree with me that they look remarkably similar. Eric? Anything to the 0 is 1. 4 to the 0 is 1. 10 to the 0 is 1. 100 to the 0 is 1. I can show you later. But you've got to have a good working knowledge of the exponent rules. But I definitely can show you. So let's look at a couple characteristics here of these graphs. So what do you notice about the y-intercept of all three of those graphs? And we in fact looked at them yesterday as well. Well, if you go back and look at all three of them, our y-intercept is at 0, 1. And because we have an asymptote in each of these graphs, which is a line that the graph approaches but never quite reaches, we never have an x-intercept. If we look a little bit more closely here at the trends of our graph, if we go back here, what we see is that we start small and we get bigger. We start small and we get bigger. We're starting at the left and we're going towards the right. We started small and we get bigger, which is an indication that all of our graphs here are increasing. That's the general trend of a graph. In terms of our domain, well, our domain in interval notation is negative infinity to infinity. I don't want us to forget the interval notation. We need to be more and more familiar as we go throughout the year with our domain. That does mean all reals, but I don't want to overlook the interval notation. X is allowed to be any value. It can be a positive value, it can be a negative value, it could be a fraction, it could be a decimal, it could be a radical, it could be 0. It could be any value. But the range is not all reals. And that asymptote helps us here, because we're not going to go below that asymptote, but we can go above it. And in fact, if you look at your graphs on the paper there, all three of them are above the x-axis. 0 is not included. So we're going to have a parentheses around that to infinity. You could also write it as y is greater than 0, but I do want us to start transitioning more over to the interval notation. And then if we look back at the graphs one more time, it says, how do the graphs change as A, or the base? I'm even going to do that. I'm going to do B, as B gets larger. Well, if we look here, I have to start back here at the blue. We're out and about there, and then we're not quite out so much, and then we're out even a little bit less, and really the way to describe that is as B increases, as our base increases, what happens is that the graph becomes steeper. And if you look back now, seeing the words, see if that makes sense to you. Because the other thing that I wrote on my paper was that this graph increases faster. Not factor, faster. And maybe that'll make sense to you a little bit more. So as we flip our page here, I'm going to skip this section right now. It's good stuff to know, but it's not imperative right now, and I think that we need our time spent more on the graphs and our characteristics. So as we look at our next function here, even though we can't quite see it, it says for each function given, fill in the table. We are allowed to use our calculators to help with this process. Then we're going to plot the points on the coordinate grid provided. So when we come back over here to our calculator, we're going to go into y equals, and then I'm going to clear this out. And this time we have 2 to the negative x. So 2, caret, and then remember, it's window, mode, and then it's that button underneath. X, comma, t, comma, theta, comma, n is our variable button. And what we're really interested in finding here is, we're really interested in finding our table. And if you look over at my table, I don't know what I was thinking when I put -3, -4, -2, -1, 0, 1, 2. But we can survive that. So I need to scroll up a little bit more here for our values. But with negative, for -3, did I type in the right function? No. When the board gets disoriented, it's very annoying. Negative x. These will give me better values. Make sure that you've got negative x as well if you were just going right along with me. We'll go to second table now. And now we have much better values to work with. But do notice that I did get out of order on this. But -3 is 8. And -4 is 16. -2 is 4. -1 is 2. 0 is 1. 1 is 0.5. And 2 is 0.25. And once we've got those values, we can draw a picture. And I know when it gets to be 0.25 or 0.111, like we had to do on one of our graphs in the last one, they get harder to graph. But do the best that you can here. Negative 3, 8. Negative 4, 16 just goes a little bit off our graph. Negative 2, 4. Negative 1, 2. 0, 1. 1.5 and 2.25. And we're going to draw our picture here. And once we get the picture drawn, the question is, do we still have an asymptote at y equals 0? And if we look close here and do the best I can to get it drawn in there, we have an asymptote. Our graph gets closer and closer and closer to that line y equals 0, but it never quite touches. So I'm going to pause the video again. I would like you to fill in B and C. Then we'll come back and we'll check our answers and look at some common characteristics before we finish these up. So as we check our answers here, there is our graph of B. When we look at this, do we have an asymptote at y equals 0? And if we draw in our line here, we do. And if we look at part C, same question. Do we have an asymptote at y equals 0? And again, what that means is we have a line that we're approaching, but we never quite reach. So there's our picture on that. And let's see if we can come up with some common characteristics here of these graphs. And they look remarkably similar to what we did yesterday. But as we flip over here, what's the y-intercept on all three of these graphs? It's still 0, 1. And because we have an asymptote at y equals 0, we don't have any x-intercepts. If we go back and look at the pictures to describe our trend here, we start at the upper left and we end up kind of lower right, upper left, lower right, upper left, lower right. All of these graphs are decreasing. And in terms of the domain, it's going to be negative infinity to infinity. X is allowed to be any value. That's our input. Whatever we pick can go in. But our output is limited. It's still 0 to infinity. And again, 0 is not included. So as we look at this last question here, how do the graphs change as B gets larger? Well, if we look at this again, it's the same kind of trend. So we're steep and then we end up pretty low. And then we're a little bit steeper and we end up there. And then we're even steeper there. But in terms of what I think I saw on your faces earlier, as B gets larger, our graphs decrease faster. So as we finish here, as we flip over to our last page, let's compare our graphs that we made in part 3 and part 1. Can we see a connection between y equals 2 to the x and y equals 2 to the negative x? And if you flip back on your paper, if we just draw we have a good sketch on the front of our paper, but if we draw a really rough sketch here of y equals 2 to the x, our picture looks like this. And it actually goes like that. And then y equals 2 to the negative x, our picture looks like that. What do you notice about those, if anything, for that matter? They're mirror images of each other. If we fold this graph onto here, we just have to flip it over. The graphs are mirror images. And you can check that with 4 to the x and 4 to the negative x. And I hope that you see the same characteristic there. Problem number 5. Let's go back to our calculators here. And it says graph 2 to the negative x, which I think I'm lucky enough I still have in the calculator. 2 to the negative x. And then let's also graph 1/2 to the x. Remember, well, we can use parentheses there. Alpha y equals, number 1, we'll get our fraction in here. 1 over 2. I'm going to close the parenthesis. Caret to the x. And when we look at this, let's draw the graph on our screen. So there's y equals 2 to the negative x. Oh, and then there's y equals 1/2 to the x. What do you notice? Let's try it again here. Let's see if I can do that. There's 2 to the negative x. And then there's the red graph, 1/2 to the x. Tiffany? Not even basically. They are the same. They're the same graph. And let's look at y. So if we look at that, it says use the properties of exponents. Well, what we've got here is we've got 2 to the negative x. I'll start with. And we just said that these are the same thing. Well, remember what a negative exponent, how it works. We take the reciprocal. So I'll put that over 1 here. We take the reciprocal of the base, which is 1 over 2. And then we change the sign on the exponent. So typically what I oftentimes write is that, changing the sign on the exponent. But especially because our numerator is a 1, we can also write it as 1 over 2 to the x. We flip and change the sign on the exponent. And there's our properties of exponents used to show that 2 to the negative x equals 1/2 to the x power. So let's go back to number 3, and let's rewrite our functions in this format. So if we look back here to our graphs, so we just solved to the negative x. That is the same thing as y equals 1/2 to the x. We flipped and changed the sign of the exponent. The process will be the same on 3b. If we look at this one, 3 to the negative x can become 1 divided by 3. We flip, which means that we change the sign on the exponent. And hopefully you even see the pattern before we get to letter C. But letter C, 4 to the negative x, we flip and change the sign on the exponent. And technically I should probably write y equals 1/4 to the x. And then to summarize, we've been exploring the exponential functions and their graphs today and even yesterday. Let's expand a little bit on the definition of the exponential functions that we talked about at the beginning of class. When a is greater than 1, so I'm going to change one thing here, because I've been talking in terms of b. When the base is greater than 1, we call this exponential growth. We've been working with increasing functions. But when b is between 0 and 1, and we call this exponential decay. If you look at our graphs, they are all decreasing. And then finally, one other common characteristic is whether we're dealing with exponential growth or exponential decay, what is the y-intercept of either kind of graph? It's 0, 1.